Hi, my name is Jeremy Wong. I'm a design engineer for signal conditioning products at Linear Technology. In this video, I'll be demonstrating how to choose a zero-drift amplifier based on some lesser-known performance characteristics. As you may know, this type of amplifier is the ideal choice for high-precision sensor circuits due to its low offset and low drift under all operating conditions. High dynamic range measurements can be made over wide common mode voltages and high closed-loop gains with excellent accuracy and repeatability. In addition, zero-drift amplifiers have great low-frequency noise performance and suppressed 1/f noise down to very low frequencies. This complete set of characteristics will allow you to reduce or eliminate the need for periodic calibration. For the most part, these devices behave pretty much like normal opamps. But in some designs, the offset correction circuitry that makes great DC performance possible may generate disruptive signal artifacts. One of these artifacts is called voltage ripple, which is a series of idle tones at the op-amp's self-calibration frequency and its harmonics. These spurious signals are generated within the op-amp and will be present even when no input signal is applied. In order to observe this artifact, the LTC 2057 and a competitive zero-drift amplifier have been configured as unity gain buffers with their inputs grounded. The output spectrums will reveal the amount of ripple that is produced in each device. Let's see what this looks like on the spectrum analyzer. The top trace shows the output of the LTC 2057, and the bottom trace shows that of competitor A. Voltage ripple in the LTC 2057 has been suppressed to below 1 microvolt RMS and should not affect the precision of your measurements or interfere with signals of interest. In contrast, the spectrum of part A contains a large number of spurs, which begin at the relatively low frequency of 6 kHz. Depending on the details of your measurement system, this level of voltage ripple may not be significant enough to affect performance, but it is something that you should be aware of. Remember that not all zero-drift amplifiers have low voltage ripple or high clock frequencies, so you should be careful when picking an op-amp for your high-precision circuits. Another artifact that you may encounter is clock feed-through. Unlike ripple, which is a type of voltage noise, clock feed-through is a type of current noise. If you are working with large source impedances or a transimpedance amplifier, pay close attention. Zero-drift circuit techniques require a set of switches at the amplifier's inputs. During each switching event, a small pulse of current is injected into the external circuit and will interact with any source, gain setting, or feedback impedances that the amplifier sees. The result will be an unwanted transient voltage at the amplifier's input. Let's try adding some source impedance to our circuit to observe the clock feed-through phenomenon. This is the same circuit as before, but I have added a 20K resistor to each DUT's input. We are now comparing the LTC 2057 to an amplifier from competitor B. Spurious signals are visible in the spectrums of both parts. However, these artifacts are much less pronounced in the 2057 circuit. For a more direct illustration of what this means, let's examine this circuit in the time domain. In this setup, I have simply taken the previous circuit and followed it with a low noise gain of 50, so that the DUT signal is big enough to see on a scope. Let's see what we get now. The 2057's trace is shown in red, and part B's trace is shown in blue. As you can see, the LTC 2057 is very well behaved, but part B exhibits a series of large transient spikes. It is clear from the waveform shape that the average value will not be zero, resulting in a DC error even after filtering. There's also the possibility that the periodic clock feed-through transients never allow the amplifier to settle to the correct value. If you are sampling this kind of signal with an ADC, the measurement will be inaccurate even if sampling is synchronized to the amplifier's internal clock. To provide a better sense of scale, this plot shows the clock feed-through transients referred to the input. For larger source impedances, the 2057's clock feed-through may introduce significant error, but at this level, filtering the output will be sufficient. Doing so may not even be necessary, however, as it is common to use the op-amp in moderate gain when measuring small signals. The closed-loop bandwidth of the circuit will effectively roll off any high-frequency transients. Clock feed-through is not specified directly in amplifier datasheets, but it is usually proportional to input bias current. In order to compare amplifiers for this particular effect, you should use the input bias current specification at room temperature and amplifier's clock frequency to get a sense of how big the charge injection spikes will be. I hope you've learned that raw offset and voltage noise specs are not the whole story behind choosing a zero-drift op-amp. You have to be aware of spurious artifacts, input bias current, and input current noise as well. The LTC 2057 was designed with competitive performance for all of these characteristics. Please check out the 2057's datasheet for more important information, such as proper layout techniques for achieving microvolt precision and some useful application circuits, including the LTC 2057 as a precision ADC driver. Thanks for watching.